This is equal to what? Mu naught times the total current enclosed. That's what we had discussed earlier. Now, Amperian loop, we didn't discuss how to choose Amperian loop. Neither we discussed how to apply or what are the steps in calculation of this. Let's discuss it. Now, also, you have to consider whatever are the charges enclosed. Charges enclosed you have to keep in mind, as in, if charges or the currents, not the charges, basically currents we have to deal with. So if currents are going out of the loop, so you don't have to consider those. You only have to consider those currents that are inside the loop or within the loop. And you have to calculate the net current that is enclosed within the loop. So according to Ampere Circuital Law, the line integral of magnetic field along a closed loop is mu naught times the total current that is enclosed by the loop. Now, what are the steps to choose an Amperian loop? Means basically how an Amperian loop should look like, or what are the conditions or properties of an Amperian loop. First one is that it should be closed. Closed, why? Because we are considering the line integral. So it should be closed. Closed, why? Because we are performing this line integral of magnetic field. For calculation of line integral of magnetic field, the Amperian loop has to be closed. Now, magnetic field should either be tangential or perpendicular to it. I'll write it down. The magnetic field should either be tangential or perpendicular to it. The reason is that it should either be tangential or it should either be perpendicular is that because when you take B dot dl, when you will integrate this B dot dl, so how do you write it? You take the cos angle, cosine of the angle, so this becomes B dl cos theta. Integrating this, so it should be either tangential or perpendicular to it. When it becomes tangential or perpendicular to it, basically what happens, yes, so when you take it as tangential or perpendicular, the angle bit becomes what? Magnetic field is perpendicular to the loop. So the angle between the normal drop to it, that becomes 0 degree. So cos 0 becomes 1 and you get this ultimately as BDL. So here you have cos theta as 0 degree. So this becomes integration of BDL. All right. And the last condition is that magnetic field should be uniform. See, until and unless magnetic field is uniform, how will you integrate it? For integration, you can integrate DL. You know how to perform integration on DL. Unless and until magnetic field is constant. If magnetic field is constant, you can take the magnetic field out of it and then you can directly integrate the length DL. So that's why, to ease your calculation, magnetic field should be uniform throughout the loop. So that when you are integrating, at least magnetic field comes out and you can integrate this integration, closed integration of length. DL integration is easier. See, if it's a circle, then DL, when all the small infinitesimal DLs get added up, that becomes the circumference of a circle. We write it as 2 pi r. In the last class also we had seen this, how to integrate DL. And all the calculations of circular, when we did magnetic, when we did that semicircular arc, when we performed that semicircle, we did what? We integrated dl, and what was the length? We did it. Now, this was a small, very small theory portion that you have to keep in mind while using it. Right now, we'll be discussing how to choose the Empirian loop. This is the condition for it. So step 1 has already been covered. Now we'll see the process or procedure to use Ampere Circuital Law. So step 1, as already discussed, step 1 is to choose Ampere. Is to choose an Empirian loop. So basically, this is a circular loop of radius, let's say r. R we are taking it. So this is basically a circular loop of radius r. This is the circular loop of radius r. This is the first step. Now step number 2, where you actually have to apply the Ampere Circuital Law. Here the application of Ampere Circuital Law is valid. We'll be using all these steps in the derivation of solenoid. We'll be using it in the derivation of toroid. So these steps will be used. So you will be able to see it. We'll do a question also. We'll do a question as well. So here it is what? What was the Ampere Circuital Law? Line integral of magnetic field means B dot dl is equal to what? Mu naught times the total current enclosed. Basically the total current that is enclosed. This is closed integral. So here we have to write it as dl. We have to write it as cos theta, b dl cos theta. Usually your cos theta will become was cos theta is 0. As I told you, you choose magnetic field that is already perpendicular to them. So this becomes what? B dl only. B dl, and magnetic field is also constant. That's why we choose such an Amperian loop. So magnetic field is constant and you integrate dl. This is what? This is the second step. So BDL till here we had already discussed. This is not new. It's just we are arranging into an order or a sequence how to perform Empirian Circuital Law, how to use it. So integration of B dot dl is basically what? Magnetic field is B. dl for a circle. Empirian loop is a circle, no? So that becomes 2 pi r. If we say the radius, what did we took? What did we take the radius? We took the radius as small r. So this becomes b into 2 pi small r. Let's say the current enclosed. Current enclosed is I. So magnetic field becomes what? Multiplied by 2 pi r. This is b dot dl. This becomes equal to mu naught I. I enclosed, we are taking it as I. So what does the formula of magnetic field comes out? This becomes mu naught I divided by 2 pi small r. This is for and this is valid for a cylindrical wire as well. See this derivation. This is the steps to do it. Now same steps you can repeat it for a cylinder if you have a cylindrical wire. So these basic steps are clear. Now see, if you have if you have a cylindrical wire, so you have to choose such an Empirian loop where the radius of the cylinder is small r. So it acts as a circle with the radius r. Then you will repeat the whole steps again. What does it become? B dot dl will be again is equal to mu naught times the current enclosed. This length will come out to be 2 pi r, current enclosed will be I, magnetic field again will come out to be mu naught I divided by 2r. So this is the formula for a cylindrical wire as well. Cylindrical wire as well. But now see, using Ampere Circuital Law, you are able to get the exact magnetic field which you used to write it. Remember, we used to write it for infinitely long wire, mu naught I divided by 2 pi. So we are getting the results again using Ampere Circuital Law as well. So on cylindrical wire, let's do a question. But before that, note down the things. Then I'll give you a question. All right. See, according to Ampere Circuital Law, integral of magnetic field along a closed curve that equals to the sum of all electric currents passing through the cross section of a closed curve, which is multiplied by permeability, means B dot dl is equal to mu naught times current enclosed. Now, to find magnetic field inside a long straight wire whose cross sectional areas means radius is what? A. Now, not only the radius in this, r is taken as what? R is taken as the radius of Empirian loop, because we have to choose an Empirian loop. No, there will be a value z. Just try it again. So when we choose this Empirian loop, the radius of the Empirian loop, we have taken it as r. As we discussed earlier, we have to first choose the Empirian loop. So we prefer the path of Empirian loop as this circle because this fitted well, and we have to find out in this region only. So a wire is there, means this whole wire. If I draw it like this, it will look, this wire is flowing, having the current I flow. So we've just drawn it elaborately. Now consider an Amperian loop of radius small r, radius of the cylinder is this. So in this area, pi a square, we don't know how much current. What did I tell you? We have to consider only the current enclosed. But current is flowing right now in this. I have just drawn it broadly so that you people are able to understand it. Otherwise, this is this wire only. The radius of this wire is a. This wire is there only. So current is obviously flowing in all this light blue portion. We have to find out the current in this dark blue portion. So see, current that is enclosed in the area. What is the area? Pi a square. So current enclosed in pi a square, this is equal to current I current is flowing, this is enclosed in this radius a. So current enclosed in the unit area, current enclosed per unit area, that becomes I divided by pi a square using unitary method. Now, can you calculate the current enclosed in this region only? Because we require what? We require only I enclosed. So now we can calculate the current enclosed. So current enclosed in pi r square will be equal to pi r square multiplied by I by pi a square. Pi gets cancelled. So I enclosed is what? I enclosed is basically, how much is left? R square I divided by a square. This much is left. Now again, taking magnetic field integral along the loop, what do we get? The same steps of Empirian loop. This was the unique part of this. Rest of the parts you people know how to do it. I enclosed was new in this part. Now you people can easily do. B dot dl will be equal to mu naught times the current enclosed. Integral of dl also you know. I enclosed right now you know. D is mu, okay, that's mu naught. It's this symbol, this is mu, and this symbol, there's a naught. So mu naught I r divided by a square by 2 pi. Mu naught I r, yes. One r will get cancelled. No, yes, correct there. Right answer. So basically this is what mu naught I will be here, a square is here. Now integration of dl for a circle, this is 2 pi r. We have done it multiple times. 2 pi small r. This is mu naught I r square divided by a square. 1r gets cancelled, and the answer is exactly what this is z answered. Mu naught I r divided by 2 pi into a square. This is the form. It's just that I enclosed was unique here. The rest of the things were the same steps. Did you write the question? Also, if there was a second part, means instead of having the field inside, had it been outside, what change will come? Can anyone tell? Any change that will come if it is outside? Means R is lesser than A in this first part, no? So it's R is greater than A. Anyone? What will be the difference that will come in this entire derivation? See, current enclosed will be different now. We calculated it for a very small, narrower region with a radius small r. If r is lying outside, means it is, just have a look before you complete this part. If this was the wire and this is the Amperian loop now with radius r, this is small a. Now I current is flowing in this wire. So B into 2 pi r will be equal to mu naught I. The total current enclosed still will be I, because total current that is enclosed within the loop is the current that is flowing through the wire. So that becomes I. So your answer will be from here, had it been R is greater than. So now this Ampere Circuit Law has basically two applications. So two application. One is a device that is known as a solenoid, and secondly we have a device that is known as a toroid. So basically, toroid is understanding. The understanding of toroid is easy because that's just circular form of solenoid connected at one end. One end is free. In case of solenoid, both the ends are free. Basically, solenoid in reality This is actually turns of isolated copper wire. If you have copper wires which have insulation coverings over them like this, and magnetic current is allowed to run, I current, let's say, is allowed to run. And each of these circular loops, no, this has radius r. So wherever in solenoid we'll be using r. This means, because we'll be drawing another diagram to derive the formula for solenoid. Because with the help of this diagram, no, the derivation becomes difficult. The derivation calculation becomes difficult. So in actual or in reality, this is actually what a solenoid. So solenoid, let me write it. It consists of number of turns of insulated copper wire. When experiments are performed with the help of bar magnet is a magnet like this rectangular cuboidal magnet, which exhibits magnetic properties, and that is inserted into this to check this some other properties that we'll see later on coil, and then we'll see inductors. So basically solenoid is this device. Now we'll draw another diagram for the derivations and the calculations, because see, magnetic fields are going inwards, magnetic fields lines are coming outwards. That becomes difficult with the help of this diagram. So for calculation of magnetic field inside a long straight solenoid, we'll be using a different diagram. So remember, magnetic field inside a closely wound long solenoid is uniform everywhere, but it is zero outside to it. Any point outside that you take, it is zero. That's why we calculate the magnetic field for a solenoid inside only. So if in the question magnetic field for outside a solenoid comes, directly write it as zero, because there is no magnetic presence of magnetic field line only outside the solenoid. So let me show you the diagram that we'll use. We use plain straight lines. This will show the upper portion, and this will show the lower portion. So let's say magnetic field lines are coming out. So let's mark this as dot. Remember we did dot for outwards. This is the symbol. For inwards, we put a cross. This is the symbol. This is inwards, that is outwards. So supposedly outwards magnetic field, because obviously magnetic field will go out like this and then it will enter it like this. So we'll draw dots for this, and we'll draw crosses to show magnetic field lines are going inwards like this. I told you, no, this is the loop, there's a coil. So this is only magnetic field going outwards and magnetic field going inwards. So these dots represent magnetic field, a current that comes out the plane of the paper, and points are marked as dot, and enters the plane of paper at points marked at cross. Now to determine the magnetic field, let's say B, at any point, you have to consider a rectangular path. We'll consider a rectangular path. Let's just name it something. A, B, C, D. We have considered a rectangular path, ABCD, as the Empirian loop, because obviously for using Ampere Circuital Law, Empirian loop is necessary. So this is ABCD is the Empirian loop. This is the Empirian. Now, Ampere Circuital Law is what? I think by now you people must have remembered it. Sneha, what was Ampere Circuital Law?
It states that the line integral of magnetic field along closed loop is not times the total current enclosed by the loop.
Perfect. Mu naught times by the total current that is enclosed. So B dot dl is basically what? Mu naught times the current enclosed by the loop, total current through the loop ABCD. Here we'll see it. So let's divide it. B dot dl for AB, B dot dl for BC. Let's divide this total. This will be B dot dl for AB, then B dot dl for BC, plus B dot dl for CD, and ultimately for this last one, that will be B dot dl for what was left, CA. This was left, and this derivation, not CA, DA, no? This is D. And this derivation comes in your exam. So derivation of the solenoid. So you have to draw this figure. Drawing this figure is sufficient. No need to draw the circular one, because with the help of circular one, the calculations do not seem clear. All right. Now see, B dot dl through BC, just have a look across BC and AD. At these two ends, just have a look at these two ends. BC and AD. What is the angle that has been made? If you look at it, BC and AD, cos theta. All of you quickly reply me in the chat box. What is the value of theta that I should take? Yes, that's right. Others? Yes, that's also right. One, two. Only two students have answered. See, it will be 90 degree. That's right. For BC and AD, that will be 90 degree. Cos theta will become what? Cos theta becomes 90 degree. Just look at the magnetic field. That is, magnetic field is either inside, moving like this, moving inside, or it is moving outside like this. And DL, your element is here, so making an angle of 90 degree basically. It's obviously difficult to show it in two dimensions, because this involves one is moving in the z axis, but you can at least imagine one is going inwards, this is outwards, field line is coming outward. So the field line is looking like this, and the wire means the Amperian loop that we have taken, BC is like this. So angle is 90 degrees. Similarly in case of this. So Hania, I think, was the first one to answer. Yes, cos 90. Hania, right. So this will be what? If you integrate C for BC part and for CD part. AD part. This will be what? BDL cos 90 degrees. And this will be also cos 90 degrees. Means this will be 0. Now what is left? Okay, okay, sir. All those who have to pray, you can come and pray. We are just doing this derivation of the solid. This will be what? BDL cos 0 degree. This will be BDL cos 0 degree here. So here it will be BDL plus here it will also be BDL. This will be BDL because this will be cos 0 degree. So for L you can be DL you can write it as L because this will get integrated. So you can write this as BL for it, and you can write for this other one, this AB as BL, and this will be what? From B to C it is 0. Then next thing we have it for C to D. Now see, one more thing is there when we are integrating it from C to D. When we are choosing this portion, no, we have to consider this wire. If we just consider this segment, we have to expand this CD. See, this CD portion, no, this part of the wire, we are considering this in air. So basically, magnetic field outside is what? This is magnetic field outside. So even when you integrate it, that becomes 0. Because ultimately what will happen, magnetic field, it is lying outside, and for outside points outside the solenoid we take it as 0 since no magnetic field is there. We are only considering this wire, right? Not the entire Empirian. So don't draw this in a CD line, just draw this as outside, so that also becomes 0. So ultimately what is left? Only BL is left. So this also becomes 0 and this was already 0. So this becomes BL. L is what? L is the length of the side AB. Let me write down. L is the length of side AB of loop ABC. Now let's say number of turns per unit length is N. Number of turns per unit length is small n. So number of turns in length L will be what? If per unit is N, then for L length, what will be the number of turns? Yes, Zaid, can you try? If N is the number of turns per unit length, then for L length, what will be the number of turns? Yes, Zaid. Samaira, can you try? Yes, Zaid. Are you answering?
Yes.
Yes,
It
Zaid.
will be N
It
per
will.
unit length will be N by L. So N equal to N by L. And we will get mu naught Ni by 2.
You not Ni by 2. No, I'm just asking you this. What should I write over here?
Ma'am, this will be N into N. N
N
into
into
N.
L. Exactly. This is what I was asking. See, number of turns for 1 unit length is small n given. So for Ln, just use unitary method. This will be n multiplied by L. So we have the value of length with us now. We can put it. Now magnetic field will be what? This becomes mu naught times, this is Bn, this is mu naught times the current enclosed. So that becomes NL times the current enclosed, because current I of the solenoid thread the loops Ni times. So L gets cancelled. Magnetic field inside a solenoid comes out to be mu naught Ni. Now that you were answering, it can also be shown that for the ends, at the ends it is mu naught ni, but divided by 2, half mu naught ni. Because at the ends, magnetic field at the ends of solenoid is just one half of the middle. We have a graph also for it. At the ends, no, which Zaid you were answering. It was for the ends. This is inside. For ends, you have it as half of that is inside mu naught ni divided by 2. Even we have a graph for it. A graph is somewhat like this. You will get a graph like this. Here it is b by 2. This is the value b inside. This is the distance that we take. And these are the ends of solenoid. These are the ends of it. All right, just note this down as well. just make a note point in this, that this is mu naught Ni, no? So if a different material is used which has a different permeability, if core of material of the solenoid that is made up of something else who has which has the relative permeability mu r, so you have to multiply that also. If material, if the core of solenoid, if the core of solenoid has permeability mu r, then multiply it. It becomes mu naught, mu r, then Ni. This also keep this in mind. Now let's do a question on this. Now, see, this question says what? A solenoid coil of 300 turns per meter is carrying a current of 5 amperes. Length of the solenoid is 0.5 meters and it has a radius of 1 centimeter. You have to find the magnetic field inside the solenoid. Now, what was the formula of the solenoid that we just derived? It was B is equal to mu naught Ni. Now, here L is also not used. R is also not used. Only the current and number of turns are used. And that too, number of turns per unit length, we did it. So number of turns per unit length is also mentioned. So is this data even useful for us? 0.5 length and radius 1 centimeter. According to any of you, do you think this data will be used in this numerical?
Yes.
How, Zed?
Ma'am, as we know, like n equal to number of turns per unit length. So we can use number of turns, that is
Number of
300
turns
meters.
per unit length is given to us.
Yeah.
See, this data is not directly used in the numerical portion for calculation. Zed, you are right. Had it been only given number of turns, 300, then you would have multiplied and got n into L. But NL, that portion is already given in by L, that term, number of turns per unit length. We use this to understand whether it's a long solenoid or not. What is the length? Length is 1 centimeter. Length is 0.5 meters. Radius is 1 centimeters. So you can see a very thin solenoid will it be like this kind of solenoid it will be, because the radius is 1 centimeter and the length will be 0.5 meters. Half of a meter will be the length of it. So half of a meter is this much at least. So half of a meter, and the radius is very small. So it tells us that this is basically what? This is basically a long solenoid. This length as 0.5 meters and radius as 1 centimeters. This shows that this is a long solenoid. And now we can use the formula. So this data won't be directly used in the numerical, but for the analysis portion, it's right. Now you can normally use your B is equal to mu naught Ni for the calculation. B is equal to mu naught Ni. Hania, how can we write mu naught? What is the value of this mu naught that I should write? Khalid,
Yes, teacher.
how to write mu naught?
B by I.
The value of this constant for the solving of numericals. Salman, is he back? Salman, are you there in the class?
Yeah, teacher. 4 pi into 10 raised to minus 7.
Yes, 4 pi into 4 pi into 10 to the power minus 7. Because mu naught divided by 4 pi is 10 to the power minus 7. Don't forget this constant. K is equal to 1 by 4 pi epsilon naught. You people are in the habit of using. So make this also as a habit that this is mu naught by 4 pi is 10 to the power minus 7. So mu naught will be 4 pi multiplied by 10 to the power minus 7. Number of turns per unit length was given 300, current was 5. So this basically becomes what? 4 into 3, 12 into 5, 60. 60 pi into 10 to the power minus 7 is there. And what about 300? This was 10 to the power 2. Just check the calculations. This becomes what? 6 pi into, this becomes 10 to the power minus 7, and this is 2 already. So this becomes 10 to the power minus 5. And the 60 is also there. No, so what was it? 10 to the power, this becomes 10 to the power minus 5 and 10 to the power minus 4 Tesla. This much will be the total value of magnetic field. One more question I am giving till the time you note down this question. This part now you people can try and submit your answers, and whatever your answer, the answers you're getting, no, just leave it in terms of pi even. That's okay. Or if you wish, you can solve it further. But at least do this question similar to the previous one, just with a slight difference. Now try this. Both of you, Zaid and Khalid, you have something missing in your answer. Till this part, it is incomplete. Just check once again. Some error must be there. No, no, not the unit Z. Apart from the unit also. I was talking about the magnitude. Yes, Tesla is definitely the SI unit, but something is missing in your answer. Samaira again. Same thing, same mistake. Take 2 more minutes, then we'll discuss. Others also answer apart from these three students. Sneha, Salman, Hania.
Teacher, I sent you my answer. Is it correct?
Khalid, This one, no, that you submitted. I told you, no, you and Z, both of you are having the same answer. Something is missing in your answer. Till this portion, it is incomplete. Just check your calculations one again. Slight error is there. Something is also along with this answer. No Z, no Z. Just check again. Ten to the power minus 4 or 10 to the power minus 3 Z. See once again. But along with that also, Z, something is there. See what is missing in your answers, in all of your answers. Z's answer, Khalid answer. Same answer is given by Salman. All of you are committing the same error. Same answer, Hania. 10 to the power minus 3 multiplied by pi. That is the answer given by all of you. 3.14 into 10 to the power minus 3. That is also pi into 10 to the power minus 3. See, this is not the right answer. What all things are given to you? Length is given, so 0.5 length is given. Radius is what? Radius is 1 centimeter. This means length is greater than radius. This shows that it's a solenoid which is long. Clear? Now, the mistake that you people are committing, see, it is made up of 500 turns. That means number of turns is 500. In the previous question that we did, we had number of turns per unit length given. Means small n was already given to us. That was 300 meters. 300, not meters, turns per unit length. So it means small n is already given. Right now we have what? We have 500 turns. Only turns is number is given. We don't have number of turns per unit length. So basically this is capital N, let's say. Small n will be what? Number of turns per unit length. That's why we write it, no? N into L. In the derivation we did NL. That Z answered N into L. So this is what? This is number of turns only given. So number of turns per unit length. Length is 0.5. So that becomes what? 2 into 500,000. 1,000 turns per meter. So number of turns now you have. Now put it as in mu naught Ni. So mu naught is 4 pi into 10 to the power minus 7. N is 10 to the power 3. And current is what? Current is 5 amperes. So this becomes 20 into 10 to the power minus 7 into 10 to the power 3. So this becomes 2 pi into 10 to the power minus 3 Tesla. Your final answer becomes, yes, 2 pi into 10 to the power minus 3 Tesla. This was missing in your answer. 2, everyone wrote pi into 10 to the power minus 3 because you took number of turns as 500. So number of turns is 500, but number of turns per unit length you have to consider. So this is the final answer. Now the second application of Ampere Circuital Law, solenoid we have discussed already, toroid we have to discuss. Now solenoid you have understood. Solenoid look like how? This was a solenoid. Now if you join it if you bend it, not joining it properly, but if you bring both the ends closer, so that is what a toroid looks like this. So from one end current is entering, it is moving into all the circular loops, and here from here it is exiting. This is a toroid. So toroid is basically what? It's a solenoid bent into the form of a closed ring. Is called a toroid. This is known as a toroid. So basically it's an anchor ring around which a large number of turns of metallic wire are wound. Now cross-sectional view, again we will not be using this diagram for the derivation of it. Toroid formula will ultimately be the same with a slight change in it that you would see, but for that let us just draw another diagram for it. So again both the lines, let us draw it in the form of a complete circle. These are the circular wires of it. So from one side current will be coming and other side current will be leaving. Let's say these are the portions where current is moving outwards. I am representing it with the help of dot. Dot symbolizes magnetic field is what? Magnetic field, these are outwards. Now let me draw cross for this. Basically this is this loop only. It's just that for the ease of calculation, we are drawing it in this way. Now we are dividing this into three regions. Firstly, let us take this. This is, let's say this is region 1. This is region 2nd and this is region 3rd. So if you choose Empirian loop for region 1st, let's solve it for region 1st. See, for region 1st, for points in the open space interior to the toroid, these are the points that are interior to the toroid. This is what? This is region 1. So in case of region 1, this is the space interior to the toroid. All right, so B dot DL will be equal to what? B dot DL will be mu naught times the current enclosed. Now, magnetic field in this region, if you take B dot DL is equal to mu naught times the current enclosed. See, DL will be what? DL is basically the length. So even if let's say the radius is small r, so what will be the circumference of it? Means length, 2 pi r. So this becomes B into 2 pi r into mu naught I. But can you see any magnetic field in this region, in this circular region 1? No magnetic field is there because magnetic field lines are associated in region 2. So since magnetic field is 0, since magnetic field line doesn't exist, so magnetic field inside this space, this becomes 0. This is here, it is 0. Now we have to take the points inside the toroid, means region 2. So region 2 is basically this region. See, this is region 2. So for region 2, you can take a circle or the Empirian loop situated here. This you can take as the Empirian loop. So let's name it as R1 so that you understand this is 2 pi into R1. Then let's take this radius as R2 so that you are able to understand this is the circle. Now let us calculate it in this region. Now in region 2 we are calculating. So region 2 is what? Let's say B is the magnetic field of this. Magnetic field is B. Capital B is the magnetic field. So now if you apply B dot dl integral, this is mu naught times the current enclosed. So magnetic field is B dl. If again the radius is R2, this will be what? 2 pi R2, the circumference. This is what? This is equal to mu naught times the current enclosed. Now see, for the solenoid, n is the total number of turns. So total number of turns in the toroid, that will be what? N. N is the number of turns in a toroid. So current won't be I. Current I is for a single turn. I is the current this is current in a single loop. So for n number of turns, what will be the current? It will be n multiplied by. So you have B as what? B becomes mu naught Ni divided by 2 pi into R. Now you have what? You have the region 3, and region 3 is this region. This is this region 3 outside. This is outside. So even if you for region 3, if you draw an Empirian loop, in the space exterior to it, like if you will draw it here, see the radius will be what? This will be the radius R3, but magnetic field line is again not there, and even for a solenoid also magnetic field outside is 0. So for region 3, directly even without writing Ampere Circuit Law, you can write it as 0. Now net magnetic field will be what? The rest of it are 0. It will be mu naught Ni divided by 2 pi R2. So let's not take R2, let's take it as R only, since only one radius is there. Magnetic field, net magnetic field becomes mu naught Ni divided by 2 pi R. Now N divided by 2 pi R becomes what? 2 pi R is the length of the toroid. Since it is curved, the length will be in circular form, 2 pi R. So this is basically number of turns per unit length. If you see number of turns per unit length, 2 pi R is what? 2 pi R is basically the length of this toroid. N is the number of turns. So number of turns per unit length, again we can represent it through small n, the way we have been using it for solenoid. So n divided by 2 pi r, we can write it as small n. That means number of turn, and small n is what? Number of turns per unit length. So magnetic fields formula will again be mu naught n. This time n has a different meaning. This is number of turns per unit length, and length is 2 pi r. So just note this down as well. And what about others? Done? Fine. Now, one last thing that we have already done, but we haven't seen its graph. See, there was a question that we did in the class. This one. Huh. See, it's said what is long cylindrical wire radius A was there, current I was flowing, where we calculated it for the inside region and for outside region was there. So this is a very important question. Just mark it as important as well. Now see, it's actually your NCRT question, a question from your NCRT only, and this has come a lot of times in your board exam. Last, I think it came in 2016, exactly the same question from NCRT. In 2010 also it came in your CBSE board exam papers. So this question is of your NCRT. Now, one thing that is here in this is the graph. Graph we didn't do. And in the NCRT, the continuation at the end of this question, there's the question says plot the graph also. See, outside when we did, inside, let's do it for inside first. R is less than A. Formula came out to be B is equal to mu naught I into R divided by 2 pi A square. Where R is what? R here is the radius of the Amperian loop. Not a Gaussian, Amperian. This is radius of Empirian loop. Now, for the region that was, this was what? This was inside. For the region that was outside, means R was greater than A. That will be directly mu naught I divided by 2 pi R. Because I told you, here the total enclosed current, I enclosed will directly be I because it is enclosing the whole current that is within the wire. So we'll write I enclosed here. Since in the previous question, R was for a small portion within the wire, in this very small portion, that's why we had to consider it and take it by unit length. Right now it is what? This is directly current enclosed, so that's why we'll write it as B into L is equal to mu naught I. L will be 2 pi R, and this will be the final formula that we'll get. But the graph we have to plot between B and R. B is the magnetic field, R is the radius of Empirian. So if you plot this, this is the graph between, on y-axis, let's take the magnetic field, and on x-axis, let us take the R, which is the radius of Empirian loop. So that I have already mentioned. Now, inside it was what? See the variation with R. First, we'll do it for inside. We always plot the graph starting from inside, R at the center, R is equal to 0. Then R is less than A, then R is greater than A, R is equal to capital R as the surface. Remember, we plotted graphs for spheres as well. Now, can any one of you answer? How is the relation between B and small r for the inside case?
Directly proportional.
Yes, directly proportional. So it will be directly proportional. Till the surface, the graph will be what? It will be directly proportional. Now, what about the second part, outside? B is directly proportional from the first part. Here you can see by this. Inversely proportional. B is inversely, P is here, R is here in the denominator. So here it is inversely proportional. So the nature of graph that you will get will be like this. So this is a part of that question only. So this was what? B is directly proportional to R. This is B inversely proportional to R. Fine. So note down these 2 points as well. And when you are done, then do text me done in the chat box. Other than Z, Sneha, Sumaira. Others, Salman, Hania, done?
Yes, ma'am.
All right, fine. So I'm stopping here today. Just revise this topic and come. This is over. Ampere Circuital Law has been completed. From the next class, we'll directly begin with magnetic Lorentz force. Fine. So I'm stopping here. Okay. Thank you.